Formula One isn't won through brute force. It's won in the microscopic gray areas between what the technical regulations explicitly forbid and what the static load tests fail to detect. What you are watching unfold right now is a masterclass in modern aerodynamic exploitation. Red Bull's brilliant wing aeroelasticity loop, how they completely outmaneuvered Ferrari's baseline downforce concept, and why the FIA's technical delegates are structurally powerless to stop it. 15 seconds. That is all it takes to see the exact tactical exploit here. Ferrari designed a rigid, highly efficient aerodynamic platform meant to maximize cornering stability. Red Bull engineered a dynamic, load-sensitive wing structure that deforms at high velocity to drastically cut straight-line drag, then seamlessly rebounds for heavy braking zones. Red Bull didn't break the static deflection tests. They engineered around the test apparatus itself, draining Ferrari's top speed advantage and leaving race control with zero legal grounds to issue a penalty. To understand why this move broke the grid open, you have to break down how flexi-wing enforcement actually works under modern FIA regulations. Under the technical rulebook, all aerodynamic bodywork must be strictly rigid and securely immobile relative to the chassis. That sounds absolute on paper. In practice, pure rigidity is a physical impossibility. Carbon fiber flexes under dynamic load. It has to, or the structural stress would fracture the component under heavy downforce. Because total rigidity is impossible, the FIA relies on mandatory static load tests in the pit lane. Technical scrutineers attach weighted rigs to the front and rear wing elements, measuring deflection in millimeters under a specified downward force. If a wing flexes less than the maximum allowable tolerance under that specific static load, it is officially certified as completely legal. Red Bull saw the fundamental flaw in that testing methodology. A static load test applies a fixed, stationary force in a single direction. A Formula One car at 320 kilometers an hour experiences complex, multi-directional dynamic airflow, high-frequency mechanical vibration, and immense aerodynamic pressure spikes. Red Bull's composite structural analysts didn't build a wing that flexes uniformly under a heavy weight in a garage. They engineered advanced carbon fiber layups with directional weave patterns that only react to specific high-speed dynamic pressure thresholds on track. At 60 or 80 kilometers an hour through a low-speed hairpin, the wing remains completely rigid, providing maximum vertical downforce. The static test rig hanging 500 kilograms off the trailing edge sees zero illegal deflection. But as the car accelerates down the main straight and dynamic pressure builds exponentially, the carbon weave deforms dynamically along a calculated rotational axis. The main plane rotates backward, opening the slot gap between the wing elements and stalling out the wing's high-drag vortex system. It acts as a secondary, fully passive drag reduction system that operates constantly, regardless of whether the car is within 1 second of arrival. Ferrari ran straight into a structural trap. Ferrari's technical department, operating under their high downforce platform philosophy, focused on absolute structural stiffness to ensure immaculate aerodynamic correlation. Their chassis yields predictable downforce, precise transient response, and excellent tire warm-up. But at high speeds, that rigid wing remains an absolute parachute. They dump drag through sheer engine output and aggressive gear ratios, which accelerates thermal degradation on the rear tires. When Ferrari realized what Red Bull was doing, they immediately brought telemetry data, high-resolution slow-motion footage, and onboard camera feeds directly to the FIA technical delegates. The footage clearly showed Red Bull's rear wing mainplane dropping noticeable millimeters at maximum terminal velocity, then instantly snapping back into standard geometry the second the driver hit the brakes. Ferrari demanded an immediate technical directive to ban the flexible structure, arguing that any dynamic movement of aerodynamic surfaces violates the fundamental spirit of the regulations. The FIA found themselves completely trapped by their own regulatory framework. Race control cannot issue disqualifications based on video footage or telemetry interpretation alone. The technical regulations explicitly state that compliance is determined exclusively by the official FIA static load tests. If a car passes those physical weight checks in the garage, it is legally compliant for the entire session. The FIA cannot simply declare a car illegal on Sunday night because a rival's camera captures the carbon flexing on a straightaway. To change the static test weights, or alter the allowable deflection limits mid-season, the FIA has to issue a formal technical directive. But issuing a new test protocol requires notice, manufacturing lead time for teams to redesign their components, and bulletproof justification that survives legal appeals. Red Bull's legal and engineering teams built this wing with full knowledge of that administrative delay. Even if the FIA introduces tighter deflection tests 3 months down the road, Red Bull has already harvested the championship points, track position, and development momentum. Why couldn't Ferrari just copy the flexi-wing concept overnight? The answer comes down to the mechanics of the F1 cost cap combined with advanced composite engineering. Re-engineering a dynamic carbon fiber weave isn't as simple as tweaking a CAD drawing or running a quick CFD simulation. Designing non-linear aeroelasticity requires hundreds of hours of specialized finite element analysis and endless physical destructive testing in structural rigs. You have to map out precise carbon fiber orientation, laying down individual sheets of carbon pre-preg at highly specific three-dimensional angles so that the material resists pure vertical load while yielding under torsional aerodynamic shear. If you mess up the structural calculation by a fraction of a percent, one of two catastrophic outcomes happens. Either the wing remains too stiff and fails to flex at top speed, meaning you wasted millions of dollars for zero performance gain, or the wing flexes too much, failing the static FIA inspection, or, far worse, experiencing structural fatigue and snapping under load at top speed. Under strict cost cap constraints, Ferrari cannot afford to dump millions of dollars into an experimental composite research project that might take 4 months to validate. Every dollar spent trying to reverse engineer Red Bull's carbon layup methodology is a dollar pulled directly away from floor development, weight reduction, and suspension updates. This dynamic created an immediate economic and operational trap for Ferrari. The development ceiling. Ferrari's rigid aerodynamic philosophy forced them to trade off top speed efficiency for cornering downforce, capping their performance envelope on high-speed circuits. The resource divergence. While Red Bull ran an optimized low-drag setup everywhere, Ferrari had to burn valuable wind tunnel hours, developing low downforce wings specifically tailored for fast tracks like Monza or Spa. The correlation risk. Trying to copy Red Bull's flexi-wing concept mid-season meant risking correlation errors between physical track testing and virtual wind tunnel data, potentially destabilizing their entire aero platform. By mastering carbon layup behavior, Red Bull gained a massive operational advantage while forcing their main rival into an agonizing budget and development dilemma. To appreciate how brutal this strategy is, you have to look at the trackside operational fallout. When a team holds a terminal speed advantage created by passive aeroelasticity, their entire race weekend strategy simplifies dramatically. In qualifying, Red Bull can run higher base wing angles than Ferrari. That gives their driver incredible grip through middle sector high-speed corners, holding tire temps in the absolute sweet spot. Then, the moment the car hits the long straights, the wing flexes, shedding the drag penalty that higher wing angle would normally carry. They get the best of both worlds, maximum downforce through the turns, and unmatchable top speed on the straights. Ferrari drivers are left in a brutal tactical position. To match Red Bull's lap times in qualifying, they have to trim wing level off their car. That makes their vehicle terrifyingly twitchy through high-speed transitions, chewing through tire tread and forcing the driver to slide through long corners. By lap 10 of a race stint, Ferrari's rear tires are overheating, while Red Bull's drivers are smoothly managing thermal wear because their wing is doing the hard work in the braking zones and relaxing on the straights. What makes Red Bull's move truly brilliant is how it systematically neutralizes the impact of the cost cap on rival teams. In the past, a team like Ferrari could simply throw a massive manufacturing budget at the problem, producing 10 different wing specs in 3 weeks until they found a composite layout that flexed identically. Today, every team operates under precise manufacturing quotas. You get a set number of wing iterations per season. If you burn through 3 structural revisions just trying to pass static load tests with a flexi wing, you run out of cap space for major underbody floor upgrades. Red Bull didn't just out-engineer Ferrari on the drawing board, they trapped them in a financial checkmate. The human element inside Ferrari's Maranello base during a technical crisis like this is intense. Aerodynamicists who spent 6 months optimizing floor diffusers suddenly find their work rendered second tier because the car is losing 0.3 of a second on pure straight-line drag. Structural engineers face immense pressure to push carbon layup tolerances right to the absolute precipice of legal failure. When engineers are pushed to design components that deliberately bend under pressure without breaking, the risk of catastrophic structural failure increases dramatically. A wing that is engineered to deform dynamically at 300 kilometers an hour is a wing that is operating on the razor's edge of structural integrity. One minor manufacturing defect, an imperceptible air bubble in the resin layup, or high-frequency oscillation from riding a curb, can turn a controlled flex into a sudden structural delamination. This is precisely why race engineers hate mid-season flexi-wing development programs. It introduces massive variables into vehicle dynamics. Drivers rely on predictable aerodynamic balance. When a driver turns into a 200-kilometer-an-hour corner, they need to know precisely where the center of pressure sits. If an aeroelastic wing snaps back into its rigid state a fraction of a second too late, or flexes unevenly because of turbulent air trailing off a car ahead, the balance of the car shifts instantly, tearing away rear grip and throwing the car into an unrecoverable snap spin. Red Bull managed to make this dynamic seamless. Their driver can lean on the platform with total confidence, knowing that the structural transition between the low-drag flexed state and the high-downforce rigid state happens cleanly, predictably, and without introducing platform instability. That level of calibration requires a masterclass in simulation software, telemetry correlation, and advanced composite manufacturing that very few organizations on Earth can match. From a regulatory standpoint, the FIA is sitting on a ticking time bomb. Every time a team successfully exploits aeroelasticity to bypass static load tests, it undermines the credibility of the technical rulebook. But the FIA knows that if they intervene too aggressively, they risk ruining the entire competitive landscape of the championship. If the FIA suddenly introduces hyper-strict, heavy-handed load tests mid-season, they run the risk of inadvertently making multiple teams' baseline wings illegal overnight. That would force half the grid to halt production on performance upgrades and spend millions of dollars redesigning basic wing structures just to clear garage inspections, an outcome that smaller privateer teams simply cannot afford under strict financial ceilings. Red Bull exploited this exact administrative hesitation. They knew the FIA's hands were tied by political consensus and regulatory procedure. They knew that by the time the FIA gathered enough consensus to implement new, mandatory load deflection equipment, the championship battle would already be settled on the asphalt. It reveals a fundamental truth about modern Formula One corporate and engineering strategy. The teams that win championships aren't necessarily the ones with the most powerful engines or the cleanest CFD models. They are the organizations that identify procedural gaps in how rules are enforced, deploy capital precisely where the regulations are softest, and force race control to fight a slow, bureaucratic rearguard action while they pile up race victories. Red Bull didn't just build a fast car. They identified a flaw in the FIA's testing physics, built a structural weapon around it, and left Ferrari holding a rigid wing in a dynamic fight. Now the focus shifts entirely to the next technical cycle. Will the FIA permanently overhaul how bodywork rigidity is measured, using optical tracking sensors and real-time dynamic load telemetry? Or will Red Bull's FlexiWing Masterclass become the mandatory blueprint for every constructor on the grid?